All right, we're looking at section 9.2, where we are going to simplify square roots. So when you're looking at square roots, there are two different ways that you can answer a question using square roots. You can use an approximation, which we talked about yesterday. We did approximations of rounding a square root to the nearest integer. We can round it to the nearest tenth, nearest hundredth, so on and so forth. Or we want to find the exact value, because sometimes we will have values that are inside the square root where if you were to type them in your calculator, you would get a non-terminating, non-repeating decimal, uh, which is an irrational number. And if you try to write it as a decimal, you wouldn't get the exact value you would get in an approximation. So when it comes to simplifying today, we are looking for the exact value. Now, one of the things that we have to keep in mind are these two properties of square roots. Basically, what it means is we can uh, put together products of values that are inside the square root and separate them. So like it's this right here is the square root of a times b, or you could write it as the square root of a times by the square root of b. These two things are the same. Same thing goes for quotient or division. You could make a fraction and you could put the square root over the entire fraction, or you could put square roots over the individual numerator and denominator. Those things are the same. Now, what you have to kind of keep in mind is which which type of strategy are you going to use to help you simplify um, certain expressions. Okay, and they kind of interchange. So um, let's look at some examples. So when we're simplifying, if we look at here, it says that a rational expression is in simplest form when no factors of an expression under the radical sign right here, this means the square root, has any perfect square factors other than 1. So anything that's a perfect square number can always be taken out of the square root and put to the outside. Okay, there are no fractions under the radical sign and no radical sign in the denominator or any fraction. Um, there are strategies in order to solve that, but I think we're okay with this one. So in this case here, we have some examples where we want to simplify these expressions. And what we mean by simplify, we want the exact answers. So we talked about discovering perfect square numbers uh, in the previous section in 9.1. Just to give you a list of a few of them, so like 4 is a perfect square number, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. All right, we made that list yesterday to help us be able to identify that those numbers are perfect square numbers. Because if we took the square root of these numbers here, we knew we would get an integer as the result. So when it comes to these values here, the first thing you have to do is, okay, is 63 a perfect square number? So I look at the list that we've made so far, and no, it is not. So what we have to do now is we have to break up 63 into a product. So two things have to be taken into account. First off, we need uh, two values to give me a product of 63. And the catch is one of them must be a perfect square number. So looking at this, I could tell you that 63 can be written as the products of 9 times 7. Now, that there are other scenarios where 63 could be a product, but the only one that makes sense is 9 times 7 because I have myself a perfect square number with 9. Okay, so what that's going to do is going to do this portion right here is now that I found a perfect square number, that can now be taken out of the square root. And we know that the square root of 9 is 3. So now that square root of 9 gets put to the outside, and my result, my exact value that's simplified, is 3 times by the square root of 7. Okay? If you look at number 26, square root of 26, you have to ask yourself, is there, well, first off, 26 is not a perfect square number. Are there two values giving you a product of 26, but one of them is a perfect square number? Well, there's only two products that I can do, and that's, well, that's 1 and 26, but that doesn't help us at all. And you got 2 times 13. Well, neither one of those values are perfect square numbers, so the square root of 26 is, in fact, in simplest form. If we look at C here, we have the square root of 15 over 16. What I'm going to do for that scenario is we have um, the quotient property of square roots, which means I can rewrite this as two separate square roots in the individual numerator and denominator. I can write this as the square root of 15 divided by the square root of 16. All right, we have a perfect square number in the denominator. I know that the square root of 16 is 4. Now the square root of 15, there's products would be 1 and 15 and 3 and 5. Neither one of them are perfect square numbers, so my simplest form is the square root of 15 divided by 4. I look at the square root of 54. Square root of 54 can be written as the product of 9 times it by 6. And I got the t squared here. Now, there are two terms that can be taken out of the square root. This 9 and the t squared, because the square root of 9 is 3. And we talked about yesterday that square roots and squares are inverse operations of each other. And so the square root of t squared will just be t to the first power. And then what's left over is the square root of 6. All you got to do when it comes to variables, as long as they're an even number inside the square root, you can always take them out of the square root by dividing the exponent by 2. So any variable, so like x squared, square root of x squared would equal x. The square root of x to the fourth would equal x squared out of the square root. If you took the square root of x to the sixth, that would be x to the third. And finally, if you had an odd number, so if like you had x to the fifth, for instance, you could rewrite this as x to the fourth times it by x, which then would equal x squared times it by square root of x. All right. That's something that you'll be able to look at in the future, but that's what we have so far. Um, Looking at these examples here, I can write this as the square root of 32 divided by the square root of n squared. N squared is a variable. It'll just be n to the first power down here. In the numerator, I can rewrite this as well, there's actually two ways to write it, but what I'm going to do is I'm going to write it as the way that's simplest. So it's 16 times 2, and then I can write this as 4 times it by the square root of 2 all divided by n. For F, this one's nice because all of them are going to be taken out of the square root because 49 is a perfect square number, 121 is a perfect square number, and the x squared will be able to be taken out. So square root of 49 is 7, square root of 121 is 11, and the square root of x squared is x. Okay? So I would challenge you to look at these examples here and give them a try yourself and see if you can solve them. Okay? If you paused it, great. If not, let's take a look and see what we can look at, what we can do. So we got the square root of z divided by 64. This can be rewritten as the square root of z over the square root of 64, which means that the square root of z is going to stay the same, and the square root of 64 is 8. I have the next example here. I have the square root, this will be the square root of 5b squared divided by the square root of 125. Square root of 125 is not a perfect square number, but I can rewrite this as the square root of 25 times 5, and this can be just written as square root of 5b squared. Square root of b squared can be written as b over the square root of 5, and then this is going to be 5 times by the square root of 5, but these two will cancel out to be 1, so my final answer is b over 5. Okay, 243, I believe, is not a perfect square number. It's not. 243, trying to find something that'll work. Okay, so I know that this is going to be the square root of 81 times 3. And then square root of 81 is 9, so this is going to be 9 times by square root of 3. Square root of 288, square root of 288 is not a perfect square number, so I got to find something that'll work. And I found something, but so since I already found it, I'm going to go with it. I know that 16 times 18 is going to give me 288. So square root of 16 is 4, so I got 4 times by square root of 18. Now, I also know that I can simplify 18 further because I know that this will turn into 9 times it by 2, and square root of 9 is 3, and 3 times 4 is 12, so I got 12 times by square root of 2. So you could have also wrote it as 144 times it by 2 and got the same answer, but it took a little bit extra step. Happens sometimes. Over here we did square root of 63 before. We know that this is going to be 9 times 7, and that's b squared. So then this will equal 3 times, oh actually, I'm sorry. This will be 3b times by the square root of 7. Uh, 7200 is not a perfect square. So 7200, I'm trying to find something that'll work. Oh, so this can be rewritten as the square root of 3600 times it by 2, and I got m squared n squared. And 3600, I believe, is a perfect square because that gives us 60. And then square root of m squared is m, square root of n squared is n, and all I'm left with is the square root of 2. Okay? So I think that gives you a good idea of what we're trying to look for here. And that is being able to simplify square roots. Hope this helps. Till next time.